In this video, we're looking at a static friction problem. So we have a block with a mass of 10.5 kilograms. It's sitting on a perfectly level surface, and we're told it feels a static friction coefficient of 0.6. Now, a force is pushing exactly horizontally against this block. And in part A, we're asked to compute the static friction force on the block. And in part B, we want the breakaway force. In other words, how hard would we have to push to get this thing to actually break loose, to overwhelm the static friction force? So the way we're going to start out is just by getting all the forces into the diagram. So here's all the forces just symbolically for the moment. We have gravity pulling down with a magnitude of mg. We have a normal force pushing up. And because there are no other forces tampering with the vertical direction in this problem, we know the normal force also has to have a magnitude of mg. So that normal force will always just do whatever's necessary to prevent a vertical acceleration from occurring. So it's there to tell us the block is constrained to the floor. Now notice that I moved our applied force, big F, to the right, and that's just because I'm more comfortable showing force vectors with the tail attached to the object. And then if we're talking about static friction, it means the block isn't moving at all, and that's because the static friction force points to the left here to prevent any acceleration from occurring in the horizontal direction. So this block is locked in place by a static friction force. Now, one of the things we need to do here is actually compute the magnitude of the maximum static friction force, so we can figure out in part A whether or not our block is going to break loose or if it's still stuck in place. So our maximum static friction force, that's given by our static friction coefficient mu s times the normal force. But our normal force in this case is just mg, and then we can plug in our numbers, and we're using a g of about 9.8 meters per second squared here. And this gives us about 61.7 newtons. So this means our static friction force can be as large as 61.7 newtons, but it can also be less than that. And it just does what's necessary to keep the object locked in place. So in this case, if we're applying a 40 Newton force pointing to the right, I know the block doesn't break loose because my maximum possible static friction force is larger than 40. So what my static friction force is going to do is just provide 40 newtons pointing to the left to keep the block locked in place, to guarantee the net force horizontally is 0. So my static friction force in part A, if we push on this thing with 40 newtons to the right, static friction force just has a magnitude of 40 newtons. Then in part B, we've basically done part B already. We want the breakaway force. In other words, how hard do we have to push horizontally to get this thing to actually break loose? That's just the maximum static friction force. If we push on this thing with a force of 61.7 newtons to the right, we're right on the cut line of overwhelming the maximum possible static friction force. All it would take is one additional billionth of a newton and this thing would break loose and begin to accelerate. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.